Hello everyone, a very good morning. So welcome to our new series of webinar on feature selection. And today with me we have Nishit who will be presenting how we can use Shapley values for selecting features for machine learning algorithms. So let's start today's session. So the title itself says feature selection using Shapley values. But even before jumping to feature selection, so whenever we develop any AI product, okay, or any data science solution we try to develop, we start basically by analyzing the business case. What is the business case there, and what we have to do? Basically, the task, right? This is the first step we do whenever we go towards developing any AI product. The next step is basically analyzing the data, doing the exploratory analysis, right? After that, we try to fix the errors in the feature. We try to re-engineer the feature, and then we go for the feature selection pipeline, right? So the main reason to have feature selection is that not all parameters or the features will contribute in creating better model or a very good performing model. So hence we need feature selection technique. So today we will be initiating our first webinar on this series, basically with the Shapley values, right? Apart from this, there are many other techniques, and yes, it does not have any order. It does not have any kind of rules and regulation. It depends on the data, right? And on what kind of models you are using. Okay. So basically, you have to try all the methods, right? People usually don't explore the methods, and they simply use 2 to 3 repeatedly used methods, and they think, okay, these two particular features or 4 5 features are doing good, so let's make a model out of it. No, it's not like that. You have to try all the methods and see which method has given you better performance. So at the end, whenever we develop any model, our agenda is finally is to achieve a model which does not predict wrong value. It should predict the correct value, right? So on this note, let me introduce Nishit. So Nishit works with me with in Rubik's, and he works as a project mentor as well, and he helps me in developing AI products as well. So this particular session will be started by him. And yes, over to you, Nishit. You can take over and start discussing the Shapley values team.
Thank you, Shivani. Hi, everyone. Before starting with today's webinar, I'd like to know, I'd like you to know that we develop ML models and ML products and projects and data science solutions on a day-to-day basis. And as you know, data has been the goal for it is the digital gold in the 21st century. So obviously we need to handle data in a better manner, and we all know how vast amount of data is being traded, not just in a day but just in 1 second itself. Like we are speaking, a lot of data is being transmitted to your ears, like as I speak, but there are a lot of insignificant things and there are a lot of important things at the same time. Sometimes you need to take in all the important things and disregard all the unimportant ones. Similarly, feature selection works in that particular way. You need not train your model based on every single feature, every single column that exists in your data frame, but you can just select few certain features. And there are a lot of methods existing to select features. Shapley Value is definitely one of them. So I'll just share my screen and we'll start with just a second. Shubham, can you stop presenting? Yeah, I hope it's visible. So we'll be starting with feature selection using Shapley values. Now, before jumping into the whole thing, first we need to know what is Shapley value, or it's sometimes also known as a SHAP value. So Shapley value is a solution concept. It's used in game theory. Now, a lot of people would be wondering what is a game theory. In simple words, basically game theory is one particular model, or you can say algorithm, that rewards certain players and penalizes certain players by taking certain features into consideration. So it will fairly distribute both the gains and costs to several actors working in coalition. Coalition means together. Now, game theory is when two or more players or factors are involved in a strategy to achieve a desired outcome or payoff. Let's say we are predicting who will be the man of the match. We also need to take consideration a lot of factors: how this player performed against this, how this player did this. So, in simpler words, if we consider in our ML language, in simpler words, it tells how certain factors and incrementing or depreciating them impacts the target variable. All right. So we'll now look into why we're using Shapley values. Now, SHAP values. Okay, SHAP is an acronym for Shapley additive explanations, and it basically breaks down the prediction to show the impact of each feature. Now, let's say you have created an ML model and you have given it to a bank who uses it to find out if a customer is appropriate to give a loan, or his or her loan request is rejected. So let's say the model says a bank shouldn't loan someone money. The bank is legally required to explain the basis of its decision. It can't just say our model predicted that you won't get the loan. That's why we are not giving. It also needs to explain why these certain factors are stopping you or hindering you from taking a loan from us. Similarly, a healthcare provider wants to identify what factors are driving each patient's risk. So let's say you're suffering from a cardiac disease, and there are a lot of tests that a certain doctor has planned out for you. But there are only a few key parameters that a doctor needs to check or have a targeted intervention, so that he or she can actually identify the ideal causative factors for your disease. Let's say it's a cardiac disease. It won't consider your, let's say, urine tests or something. It'll just consider your cholesterol, your BP, or the other important factors. So this is one of the most convenient ways to select top features, Shapley values, in a linear model, and it may involve linear regression or logistic regression. It will also be implemented in random forest regression (SVMs), and it basically can be involved in models which involves numerical coefficients and weighted distributions. So yeah. Now, how do we use this Shapley values? SHAP values will interpret the impact of having a certain value for a given feature in comparison to the prediction. Now, let's say we have a prediction and we have a lot of predictions that a model has made, and there's an average or baseline prediction of that particular value. Now, we need to calculate its entropy change of each feature, which is given by delta G, and this Shapley function is given by phi I g is equal to 1 by n factorial summation of pi belongs to this whole formula, this gigantic formula. We need not consider this because in Python, the library itself calculates the SHAP values of all the features. Now, given a characteristic function game G, here you can consider your game to be a model M, and Shapley value of a player I, you can consider player I as a feature number 1, feature number 2, and so on. So in this way, it calculates all your SHAP values in your Python. Okay, I'll tell you the interpretation of SHAP values, like how do we interpret the SHAP values when we look at our IPyNV files. So to use SHAP library, obviously you need to install SHAP in your working directory, be it collab or your local host, your local system. You can use pip install SHAP and install it. And if you want some reference to the library, like how it works and what are all the features, there's a GitHub link of the founder who actually created SHAP library on Python, and you can look into it. So we'll move on to the demo, that is the IPyNV of how SHAP values are working. So cool. Okay. Now we have installed SHAP, as you can see. So after installing SHAP, we'll now import dataset using the SHAP function. Now, SHAP library also has features to import dataset. Okay, so we are importing dataset, the iris dataset for a simple explanation of how SHAP values work. After that, we'll move on to Boston dataset. So we have imported the iris dataset, as you can see, sepal length, sepal width, petal width, and these are all used to predict what kind of flower it will be. So this is a basic, simple iris dataset. Okay, so now we'll implement a SVM model basically on it, and we'll create a prediction we'll predict all the like flower types from all these parameters. Now after we have predicted all our parameters, now we will now use the SHAP library to calculate which all factors are incrementing the target variables, and which all factors are decrementing the target variable, which is positive impact of a feature on a target variable and negative impact of a feature on target variable. Now the blue color, if you ever plot a Shapley plot in your like working directory, blue color always means it's negatively impacting your Shapley, your target variable, that particular feature and its particular value. And if it's a red color, that means it's positively impacting. That means it's incrementing your target value. Now we have here petal length in cm, let's say 4.5. It's petal length petal length of 4.5 centimeter is basically negatively impacting your negatively impacting your target variable. But a petal length of let's say 1.4 cm is positively impacting your target variable. So this might seem a bit confusing, this graph, but this is how basically SHAP functions work. So this is how you can use to figure out how SHAP functions are SHAP values of certain features are impacting your target variables. Now you must be wondering, how do I interpret this and select features out of it? Because that's the whole point of using this function, right? So to do that, we have to definitely.
Sorry to interrupt you. There's a one question from Shubham. So let's answer that and then let's move forward.
Yeah, sure.
Yeah.
On y-axis, is it delta G value? Y-axis, we have the SHAP values of that particular variable. Okay, the SHAP value of all the particular variables is given on the y-axis. I'll show you another example, because this might be difficult to interpret, since it's not a normal plot, it's a forced plot. I'll show you in another dataset how Shapley values are impacting your model, and how to interpret Shapley values. So we'll look into another file, like another data set. Let's say we have so we are loading our Boston data set over here. Now we'll be using a simple random forest regressor to train our model. Now we are importing using the simple, after importing all the libraries, we are importing our Boston dataset and loading it into all the feature names into X. So basically, our X will contain all the feature names of the Boston dataset, and Y will contain all the values from our target column, that is median value of the data set. So our Y will contain the median values of the housing price data set, Boston data set, and our X will contain all the feature names. Okay, so after that, we will create a DF Boston data set which consists of all the X variables, and at the end there's a target variable. Okay, so this is our data frame to be trained. Now we will train our random forest regressor on X and Y. Now X consists of all this crime, ZN, Indus, chassis, NOx, RM, age, dis, RAD, tax, PT ratio, B, LStat, up to till LStat. All these variables are included in our X. Okay, and all our other remaining, that is only one target, is our Y variable. Okay, now we'll fit our model based on X and Y. Now we are not splitting the data set here, as you can notice, because we are training it. It's a small data set. We're training it on 100% of the data. So after we have done training our model, we will take input from a user and predict the value based on that model. So I'll just first I'll go through the code, and then we'll run and see what is happening. Okay. Now here I've just entered random values. This is where we put in our inputs. This function is defined here, def user input features. This is defined here to take in inputs. of all the X variables that we have. After we pass in the inputs, we will be predicting what is the median value based on that input. So now we'll have a model random forest regression model. Now prediction, the model will predict what we've passed over here, all these values, and it's giving a prediction of some 35.346 or something. Okay, so we will pass like over this code again, and I'll show you how it works. Now this explainer, we are defining an explainer variable. Now it is a SHAP tree explainer. Okay, so it will basically explain the model of how certain features are impacting certain values. Okay, certain target variables. Now we'll print our feature importance, and we'll give this particular SHAP value based graph. Now this SHAP value based graph, you'll be noticing a lot of reds and a lot of blues. Now you must be wondering, how do I interpret this basically? So a red means a high value, a high SHAP value and high impact on your target variable, high positive impact. And blue means a high negative impact. Now you must be seeing the ones which have high red values and high blue values, they are impacting your model in a very impacting your target variable in a large fashion. Like they are impacting your model the most. Basically, the LSTAT, RM, DIS, crime, these all are impacting your model more than how the lower placed variables, let's say ZN, CHAS, RAD, these will impact. Now we need to see sometimes this may also be difficult to interpret, where is red, where is blue, how do I make sense of it? But this basically automatically, this library will automatically organize all these variables based on their increasing to decreasing order. Else that is the most important feature based on SHAP values. RM is the second most, this, and up until ZN. ZN is the least important. So instead of that, you can also put a summary plot of all the SHAP values. Now, when you have a summary plot, it will show you all the SHAP values and how the magnitude is having an impact on the model output. So the LSTAT, as you can see, is having the highest SHAP value, then followed by RM, DIS, crime, NOx, PT ratio, and further on. Now you can see LSTAT is the most important feature in your particular model. And after that, you have RM, you have DIS, you have crime, you have NOx, that is a pollutant. If you have a question, if you have more features, what is figure number? What is figure number should we select? If we use, if we have, okay, are you asking how many features we should select? Because that's again subjective. That's again a subjective thing. Like I said, here you have 12 or so variables, if I'm not wrong. Now LSTAT and RM and DIS are the most important features based on the SHAP value. So you can drop ZN and CHAS and then see how it's impacting your model. I'll show you how it will impact your model, and then you can do your model training based on the remaining columns. We have another question. Here LSTAT needs to be dropped because it's highly correlated. No. Correlation factor is entirely different from SHAP value. Okay. Pearson correlation coefficient, like in heat map. Yes, absolutely. This is kind of related to that, but I'll tell you where it is different. Okay, here in Pearson Pearson correlation heat maps, you calculate correlation factors, and the ones which are high, which are having high correlation factors to the target variables, you basically drop them. All right, because it's highly correlated to the target variable. But here, based on the SHAP values, the highest SHAP values are the most important features for your model. You can't discard them, because if you discard them, then your model will predict random things and will have a high error, and the accuracy will be very low. So the LSTAT, RM, DIS, these are all having high SHAP values, and these are the most important features for your model. So you need to keep that in mind, not to discard them, but to consider them. The low SHAP values like ZN, CHAS, these are all the attributes, these are all the features that you can ignore. Drop from your model. If you think that the model is taking a lot of time, you can drop these columns. Okay, got, yeah, fine, cool. LSTAT and ZN are most important features. No, LSTAT, RM, DIS. Okay, feature import. Like you can see the heading of the chart, feature importance based on SHAP values. LSTAT is the most important. followed by RM, followed by DIS, followed by crime, followed by NOx. The least important are ZN, CHAS, and yeah, further on. So yeah, basically increasing to decreasing order. So yeah, we'll continue with the Boston dataset. Now we have gotten how our basic features are being which are all important features, which are not important features. So now we'll load the dataset again. But here you need to see a key difference from the earlier time we loaded the dataset. We are dropping the column ZN. Okay. Now we are not taking this ZN because our Shapley values graph is telling us that ZN is not that important. It won't affect your model if we drop this. You can also drop in further columns like let's say you want to drop CHAS, then you can also drop like RAD. Okay, RAD is somewhat important, but let's stick with just dropping ZN as of now. Okay, so after dropping ZN, we'll again train the model. And then we'll do the predictions and find out how other factors impacting. So now we'll run this entire entire IPyNB and see how it's working. So yeah, now this is the first instance where you are including ZN. Okay, this is the first model where we are including ZN and are not dropping it. Okay, so let's just enter random values 12, 12. I'm basically entering 12 for every single variable. You can enter your own variable, but just keep it same so that you can compare the value with the predicted value when you're dropping ZN. So tax is 12, PT ratio 12, B is 12, and stat is 12. Okay. So we have passed all the values as 12. Now it's coming after we have passed on all the values as 12. The prediction is coming as 35.257. Okay. And these are all the SHAP value functions, which also include ZN. Now we will drop this ZN axis. We have dropped this ZN from our data frame and then train the model. Like see how, if at all ZN is required to train the model, or we can just simply drop it. So after that, we'll train a random forest regressor again on that. And now we are not taking an input of ZN. We have basically dropped it. So we'll again pass on all the same values, 12, 12, 12, 12, 12, and so on. Okay, we have passed on all the same values, 12. Now you can see the prediction. Okay, the prediction is not that different from what it would have predicted if you would have taken the ZN feature. We have dropped the ZN feature and it's predicting 35.022. Okay, and in this case, it's predicting 35.257, which is like this much marginal error is fine. But and you must be wondering, why am I trading off one column just because I need to just because to land with the same values but a bit lower? Why am I trading off this column? I can simply train it because it's not taking that much time. Correct. When you have a small data set, you will always have the liberty of taking all the columns. And this is a small data set. This has only 506 rows and 12 columns. But at times when you have, let's say, 20 columns and 1 lakh rows, at that time you can't consider all the features for training a model, right? So that's where you need to take the important ones and discard the least important ones. And after you discard the least important ones, you will get to know that okay, it wasn't impacting your model in that radical manner that you wanted it to be. So now we'll see, as you can see, the SHAP values, we don't have ZN anymore because we have discarded ZN from our model. Similarly, now the least important one is CHAS. Similarly, you can train this model again by dropping the CHAS variable. Like I said, where we are dropping ZN, you can just do a comma and then drop CHAS and remove taking input from here and CHAS, and this also you remove and then train. You'll find similar results because these are the least important features based on SHAP values. So after you've done predicting all these values, you've gotten your SHAP values. You can discard the ZN in CHAS and the least important ones when you have a large data set, and then do another prediction and finalize that as your main model. Now, the simple logic behind this, like I gave you an example, when you're creating a model and using it for commercial purposes or for medical purposes and all, sometimes your model will come to a decision that okay, this is true, or this is I need to do this. This model needs to do this. We'll reject this candidate or something like that. At that time, you won't have the liberty of telling people that the decision was taken by the model and hence it is the final. You will be obligatory that you will be required to give an explanation as to why that model did this prediction. This is where you can use SHAP values like totally reliably, because it will tell you that okay, these are all the important features and these are all the parameters that you're not fulfilling, hence you are not being given a loan, or hence you have this disease or something like that. So yeah, after doing that, you'll like get to know which are all your important features. So yeah, questions if any, I'll take them now. Yeah, SHAP is not telling about directly. I mean LSTAT is equal to. Is not telling about directional relationship. I mean LSTAT is highly positive or highly negative. Okay. Okay, it's not telling you a directional relationship. Okay, I get it. This SHAP value is basically telling you how important a feature is. That's it. It won't tell you highly positive, highly negative. This summary plot, but highly positive and highly negative will be determined by this SHAP plot that you have over here, and the force plot that I was showing you earlier. Basically, blue means it's negatively impacting your prediction. Let's say your prediction wants to predict by taking all the features. Let's say your prediction, like your model wants to predict a value to be 30, but if it's entirely in blue, like your SHAP function, and it's having a low negative SHAP value, then it is telling your model, okay, this is not 30, this is maybe 29 or 28. It's basically decrementing your target variable by a certain notch. And if it's positive, it is telling, okay, your prediction is not 30, it might be 31 or 32. So that's how it's impacting. Now, when we take the average of all the positive and negative values, we'll get, okay, what the actual model is predicting, like, or is trying to predict of all the features. There's another question: if SHAP value is small, can we drop it? Absolutely, you can. But like, let's say you want to drop PT ratio, NOx, and all these. These are definitely smaller than LSTAT and RM, but still, then these are very important features to consider. You can't just drop all the features, but features like having like ZN, CHAS, uh, these are all very like minute features, like you can say, not that important when you have a large data set. So if you have a very large data set, you can definitely discard ZN, CHAS, and the insignificant features. Please brief about other methods for feature selection within SHAP. Okay, there are lot of methods for feature selection. There you can use random forest random forest for feature selection as well. But all these feature selection methods will definitely be covered further on in our other webinars. So you have to stay tuned for that. Yeah.
Let me add more to your answer for the question which is asked by Shubham. So Shubham, basically, see how we start with the feature selection, if you really ask us. So we first start by removing the constant features. We start removing the unwanted features like unique value features. We first remove them because they don't provide any kind of information, and we simply remove them. Right. After that, what we do, we check for the highly correlated features. If I have highly correlated features, I will remove them. Okay. So if you are clear with these two steps, then afterwards you can take any method. As Nishit said, you can take SHAP values, you can take random forest feature importance, right? Going forward, we will cover with standard methods also, backward elimination, forward feature selection methods. So these things you can take care from there. Okay. Over to you, Nishit.
Any more questions? How can we know? Is there any threshold value? No, there's no threshold value to drop SHAP values. In random forest, you have threshold values, but here it's purely like your discretion if you want to take in certain features or you want to discard certain features. How can you know the SHAP values are linked between IV and DVs? I'm not really sure what you mean by IV and DVs. Okay, basically independent and dependent variables. Oh, okay, fine. How can we know the SHAP values are linked between? For that you need to. This is just this is just how it's related to your target variable, not the other variables. For know that link between IV and DVs, you can do a simple correlation heat map. You can get to know if they are interrelated and interdependent. You can just chart a correlation heat map and get to know that. This is just feature importance based on your target variable. No, you can't use it for categorical features. That's why I said when you have numerical and weighted features for predicting your target variable, then only you can use feature selection for okay. If not, what is the alternative? Okay, so basically you want to know how you can do feature selection with categorical variables, right? See, you can do chi-square test, if I'm not wrong. If you can use chi-square test for selecting features from categorical features. Obviously, these will be covered further on, but for numerical and for weighted based features, you have to take you have to need, you can take any feature selection method, but you can use SHAP values. For others, you can use chi-square tests and yeah, a lot of other things. Or SHAP scaling is a must. No, it's not. No, it's not required. You can just pass it in. You can pass your SHAP function in to your data set, and then you can figure out which features are important. Basically, you need to first make a prediction. After you made a prediction, it will generate SHAP values based on those predictions. Scaling is not required. How to take care about the weight assigned to the features? See, here you have not assigned any weight at least not in this example. But like I said, you need not consider take care of the weights assigned to the features. Rather, you need to consider this. Basically, your SHAP function is basically a way of determining how weighted is your feature when compared to your target variable. So if you're considering let's say LSTAT, RM and all, these are obviously weighing in more for your target variables. So you need not take care about the weights assigned to the features when you're considering SHAP values. You just pass on the raw data set and your prediction, and then it predicts, okay, these are all the features which are having a high impact on prediction. These are the features that are having a very low impact on your prediction. Data set, why you need to predict more models if one model can provide answer? Okay. See, there is no one model to predict every single thing that exists in the field of data science. You will have, let's say, this Boston data set, simply predicting the median value of this. There will be that I know of, there will be 11 or 12 models, and obviously other models will exist, like some 200 or 300 models you can use to predict this median value of your house. So in data science, there will be 20 different models for one simple problem, and at the same time there will be one model for 20 different problems. It all depends on what is your prediction and what you're trying to predict. So there's definitely no one model, one solution to every single data science problem. So yeah, thank you so much thank you for joining, Davut. This is all mine. The first side where SHAP formula is written. Okay. This one, right? Yeah. So here, like I said, so given a characteristic function game G, for us, we won't consider this game as G, rather model M. Okay, so here we're not, since this is this formula is from a game theory, it's not based on machine learning, this is from game theory. The Shapley value of a player I, let's say one player exists I, here we can consider this player I as our feature I, or feature 1 or feature 2 belonging to N. N is the number of features that we have. That is given by phi ig is equal to 1 by n factor, modulus of n factor. N is basically the magnitude, the number of features that you're having. Because n is your magnitude. It's basically telling that this is the number of features that we have. N is features. It is positive always. Yes. Yes, obviously. It is positive always. See, this formula is derived from game theory. Yeah, exactly. What I'm saying is this formula is derived from game theory. This is not based on your ML model. So definitely your N is not definitely N will be negative in game theory. It can be negative. We obviously have no idea if it's negative in game theory or not. But for us, N is always positive since it's the number of features that we have. Is it required to balance the data before? No, it's not. It's not required.
Okay. Any other question, guys? What is the threshold value to drop the variable based on SHAP values?
Oh, we have discussed that.
Discuss that? Okay, fine. So guys, in your Zoom chat, I have shared you the code link. Okay. So Nishit, I would request you to share a little more study material on SHAP values as well as the GitHub link you have shown, so that after this session can go through it again and they can use the reference code which we are providing in their implementation.
Sure. Yeah, I'll share the slide.
Yes, the Google Drive which we have shared, in that we'll share the slide as well.
Yeah.
Okay, module wise practical will be done simultaneously. Okay, so if you don't have any questions, so let's close the session. And yes, the next session will be again on feature selection. So please do join and yeah, get to know what are the other ways of doing the feature selection. Thank you so much everyone for joining this session. See you in the next.